This head-up display works because it projects crucial information directly into your line of sight. The clever bit here is that it allows you to see data without ever looking away from the world ahead. Traditionally, pilots or drivers had to angle their heads down to view instruments. HUDs keep the head up and eyes forward, a simple yet profound change. Even more critically, a HUD means your eyes don't need to refocus when shifting between the outside world and the displayed data. This is a key advantage. Early attempts at transparent displays might have simply projected an image onto a piece of glass. While visible, this often created a problem for the user's vision. The issue was that the projected image, being physically close to the eye, still appeared near. This meant the user's eyes would constantly have to refocus. This constant refocusing, known as accommodation, causes eye strain and delays information processing. It defeats a core advantage of the head-up concept. Furthermore, a simple projection might lack sufficient brightness or contrast to be clearly visible against varying outdoor light conditions, especially bright sunlight. The image could also appear ghosted or doubled if the transparent surface had multiple layers, creating distracting artifacts instead of a single clear display. These limitations meant that simply shining light onto a transparent surface wasn't enough. A more sophisticated optical solution was required to make HUDs truly effective. To overcome these challenges, engineers realized they needed to make the projected image appear as if it were much further away, ideally at optical infinity. This required a specific optical technique called collimation. Collimation makes light rays parallel, effectively tricking the eye into perceiving the image as distant. By using a combination of lenses and mirrors, the light from a small display could be manipulated to create this distant virtual image. This virtual image would then be reflected off a transparent surface, like a specially coated windscreen, into the user's eyes. The special coating on the windscreen, often called a combiner, is designed to reflect the projected light while remaining highly transparent to the outside world. This optical arrangement ensures that the user perceives the data as if it's floating far ahead, perfectly aligned with the distant view, eliminating the need to refocus. The bigger problem is the counterintuitive engineering required to make a physically close projector create an image that appears to be at optical infinity. It's not just about projecting light, it's about manipulating light rays so they behave as if they've traveled a vast distance, even though their source is mere inches away. This optical trickery is crucial. Without it, the HUD would simply be another close instrument, negating its primary ergonomic and safety benefits.
Another challenge is maintaining the precise alignment of this virtual image with the real world, even as the user's head moves slightly or the vehicle vibrates. This requires sophisticated tracking and calibration systems, which are a subset of the features needed for full augmented reality, but still complex for a HUD. So, the core engineering challenge is to reliably create this distant, stable, and perfectly integrated virtual image from a compact, physically close projection unit. The methodology begins with a small, high-resolution display, often an LCD or DLP panel, which generates the raw information to be shown. Light from this display then passes through a series of optical elements, starting with a collimating lens. This lens is the heart of the distance illusion. The collimating lens takes the light rays, which are naturally diverging from the small display, and bends them so they emerge parallel to each other. When parallel light rays enter the human eye, the eye's lens does not need to adjust its focus. It perceives these rays as originating from an infinitely distant source. After collimation, the parallel light rays are directed towards a combiner. This is typically a partially reflective, partially transparent surface, often the windshield itself. The combiner reflects the collimated light into the user's eyes, creating the virtual image. Simultaneously, it allows light from the real world to pass through. This is why the display appears transparent, allowing the user to see both the data and the outside environment without obstruction. The virtual image is precisely positioned by the optics to appear at the same focal plane as the distant external environment. This is the core of the no refocusing benefit. To combat ghosting, specialized windshields or combiners are often used. These have a wedge shape or specific coatings to ensure only one clear reflection is seen. Brightness control is also critical. Sensors detect ambient light levels, and the HUD's projection intensity is adjusted automatically to maintain optimal visibility. Some advanced HUDs incorporate eye tracking technology to ensure the virtual image remains perfectly aligned with the user's gaze, even with head movements. This dynamic adjustment prevents the image from appearing to swim or shift relative to the outside world, which would be highly distracting and counterproductive. The entire optical path from the display source to the combiner must be meticulously designed and calibrated for precise image projection. Any slight misalignment or imperfection in the optics can lead to distortions, blurring, or incorrect placement of the virtual image, compromising the HUD's effectiveness. The choice of display technology also impacts performance. Modern HUDs often use micro-LEDs or DLP projectors for their brightness, contrast, and compact size. These technologies provide the high luminance needed to make the projected image visible even in direct sunlight, overcoming one of the initial setbacks. The entire system is housed in a compact projector unit, often integrated into the dashboard or overhead console, making it unobtrusive. From military jets to luxury cars, the fundamental optical principles remain the same, adapted for different environments and user needs. This intricate dance of light, lenses, and mirrors is what allows a HUD to seamlessly integrate digital information into our real-world view. From its origins in military aviation, the head-up display has evolved into a sophisticated engineering marvel. Its core benefit remains the ability to present critical data without forcing the user to divert their gaze or strain their eyes by refocusing. The counterintuitive engineering mechanism, making a physically close display appear at optical infinity, is achieved through precise collimation and reflection. This optical trickery is what truly sets HUDs apart. By solving the bigger problem of creating a stable, distant virtual image, engineers have significantly enhanced safety and efficiency across various applications, from piloting complex aircraft to navigating busy city streets. HUDs represent a crucial step towards fully immersive augmented reality, demonstrating how virtual information can be seamlessly integrated into our perception of the real world, making complex tasks simpler and safer for everyone.